So we're going to talk today about friction. We looked at this last year, so we're going to go a little quicker, but what's friction? Honestly, there are several different possible explanations. Grace, this is one explanation that works and satisfies what we see and allows us to make predictions, but it might be wrong. One possible explanation for friction is that it's due to the interlocking of molecular hills and valleys between a surface and an object on that surface. Although surfaces might appear smooth on the atomic scale, they are not. You can try this experiment if you want right now. Put your hand against your lab table, push down and pull towards yourself, and you will feel a force resisting you. Even though your lab table seems fairly smooth, there are microscopic hills and valleys that are intersecting with the microscopic hills and valleys on your skin and applying a resistive force. So if you zoom in, yeah.
Is that why Velcro works so good?
Velcro, there's actually more physically going on. On one area of Velcro, if you zoom in, there's a whole bunch of hooks, thousands and thousands on them. On the other area of Velcro, there's a surface that I think has V's, and the hooks hook into the V's, I think. Okay? So I can't call that friction, although honestly, no, the reason I can't call that friction is I don't think Velcro depends on the normal force. I don't think. Once you press down on it, you don't need to keep applying a downwards force. Yeah, also because Velcro is able to resist against you can put it against the wall, and my free body diagram there, friction would not be the force that I could use to make that work. So good question, but no. So if you zoom in, that's what you would probably see, we think, maybe. The key idea, Kyle, is that friction resists sliding. That's the direction. What that means is it can resist motion, which is the most common form, Jack, but it can also cause motion, especially if you're talking about a car. If a car is moving, friction is going to point in the direction that the car is moving, usually. So example 1 says, draw the direction of friction in each case. Situation number 1 is a sliding block. There's a slight typo here. These notes were typed up in Word 1995 for Mac. They're old, and the diagrams are slowly deteriorating. And so that little white space between the blocks and the box and the floor should not be there. Sorry, I can't fix it right now. Anyways, so imagine that gap isn't there. Which way is the block sliding? To the right? Which way would friction be pointing? Which way would friction be pointing?
Backwards. To the left.
Good. Good morning, good morning. I'm so glad you made it.
Is it morning?
The really tricky one is the next two diagrams. A car speeding up. People want to think that the force that makes a car speed up is F engine or F tires. It's not. Although, by the way, if it was F engine or F tires, cars could drive on ice just fine. It's friction. Now, why is it friction? Well, if you look at this tire, right where it contacts the road, the tire is pushing backwards against the pavement. Forces come in. So if you push backwards against the pavement, what does the pavement do? Push forwards against the tire, which is attached to the car. And that pavement pushing forwards force is friction. That's what makes a car go forwards. Nothing else. Now, then you want to ask, Mr. Duick, what does the engine do? The engine is what causes the tire to spin to apply the force backwards. And so you do need the engine to make the tire spin. But I'm telling you, if you spin tires on ice, you're still not going to move forwards, even though you've got the force making the tire spin. For a car slowing down, well, when you tap on the brakes, what you really do is you make usually the front wheels or sometimes all four wheels slow down. They try and push forwards against the pavement. Forces come in pairs. If the tires push forwards against the pavement pushes backwards against the tires and the cars that they are attached to. Friction points backwards. We said last year that the amount of friction depends on two things. Grace, we said one of the things that it depends on is how sticky or slippery the two surfaces are next to each other. We called that the coefficient of friction. Symbol, Greek letter mu. We said that a higher mu meant stickier. A lower mu, a smaller number, meant slipperier. Usually mu was a decimal between 0 and 1, although we'll talk about situations where mu can be larger than 1. But usually mu, the coefficient of friction, was a decimal between 0 and 1. It doesn't have any units. It's a dimensionless quantity. Sorry? No units. So if I ever ask you to find the coefficient of friction, you don't put units next to your answer. It has no dimensions. Just for some rough guesses, steel on ice has a mu, a coefficient of friction of about 0.01, really slippery. Rubber on concrete has a mu, a coefficient of friction of about 0.25, fairly sticky, fairly grippy. The second thing that friction depends on is sort of how heavy an object is. We agreed that bigger objects are tougher to slide. But we also last year wanted to account for the fact that if you lift up as you're sliding something, it gets easier to slide. And we said, well, the mass of the object isn't changing, mg isn't changing. Who remembers friction depended on mu and which force? The normal force. We said a much better indication of the force between two objects that push each other together was the normal force. And so in the box here at the bottom of the page, you can write friction equals mu times the normal force. I don't know the normal force, and there is no equation for the normal force. Oh, but look, you'll have to do a free body diagram to figure out the normal force. Oh, and while we're at it, what if I asked you to find the coefficient of friction, mu? How would I get the mu by itself? More specific? And answering your question from earlier, Manchan, when you said, what do you mean by dimensionless? Can you see we would get newtons divided by newtons? The units would cancel. Dimensionless, no units. Mu is a ratio, but no units. Let's look at example 2. So consider the block below, and it's being pulled by student number 1 across a rough surface at a constant speed. I've probably underlined the phrase constant speed. That's probably fairly important. Suddenly, student number 2 pushes down on the block with a force F. You know, let's quantify this just a little bit. Let's say instead of a block, how about the big wooden benches in the gym? The ones at the back of the gym that you can slide around? Okay? So let's say that Matt is pulling one of the benches across the gym at a constant speed, and then suddenly Davis decides he's going to sit on the bench while you're pulling it. Okay? What happens to the weight, the normal force, friction, and the motion of the bench? You know, just to make this organized, let's call that part A. Let's call the normal force part B, friction part C, and the motion of the bench part D. So you got the analogy? You're pushing a bench along the gym at a constant speed, and then one of your friends comes and sits on it. All right. The first thing this asks is, what happens to the weight? When I say weight, what force am I actually talking about? mg. Does the mass of the bench change when you sit on it? Not the overall mass. Does the mass of the bench change when someone sits on it? So does the weight change? No change. What does change? You know, now I think maybe we better do a free body diagram. I noticed they gave us one on the left. So let's do our free body diagram. Here's when we have the extra push down. Here's when somebody is sitting on the bench on the right. What are the forces acting on this? Get the obvious one. So we definitely have mg down. Is it sinking into the ground like quicksand? Is it flying like Superman? So what has to be pointing up? Is the normal force bigger, smaller, or the same size as mg? And how do I know? Pardon me? Convince me. Oh, we got two forces pointing down. So are we sinking in the ground like quicksand? Are we flying like Superman? No. Then everything down has to equal everything up. So the normal force is canceling out mg, and it's canceling out the extra push of your friend. And I think that will allow us to answer part B, Owen. What happened to the normal force between these two pictures? Increase, decrease, or stayed the same? My abbreviation for increase is an arrow pointing up. Do you know what my abbreviation for decrease is? An arrow pointing left. Down! Oh, that's way better. Down. I'm using that. Okay. Marcella, from the box down here, friction is what times what? Yeah. So if the normal force got bigger, part C, what must have happened to the force of friction? Bigger, smaller, or stayed the same? Bigger. So I'm going to add friction to my free body diagram, and you said it got bigger. So here's my question then. What happens to the motion of the block? Or in my free body diagram, which way are we accelerating? I don't know what that means. Left? So which way were we moving? To the right? But which way are we accelerating? To the... So are we speeding up or slow? We're going to slow down and eventually come to a stop. But let's say we're talking about the split second after your friend sits on it. Because once it comes to a stop, our free body diagram would change a little bit. We'll talk about that later. So I think we can safely say... And where it says explain your answer using principles of physics, I think our free body diagram is a pretty good explanation, I think. I hope. Is that all right? So friction is what times what? Mu times the normal force. How sticky an object is times how hard the two surfaces are being pressed together. Does the next question on the next page have an A and a B and a C for us to pick from, or and a D? Is this a voting question? Oh, it is! Excellent. Example 3. A student gives an old shopping cart a big push on a flat, rough surface. Which of the following is the best free body diagram for the cart after the student has released it? I don't have a shopping cart here, but I do have my big little office chair, teacher chair here. So what we're talking about is right after I let this go, after pushing it, but before it comes to a stop. What's the best free body diagram right now? But not right now. Once again, we're going to vote. Once again, how high we hold your hand up is how sure you are of the answer. I'm positive. I'm pretty sure. I'm only guessing. Okay? Got the argument? Oh, and the direction of motion is to the right, I guess. Who says A, Mr. Dewick? A. Who says no, Dewick? It's got to be B. C. D. Who didn't vote? Sorry? So I'm putting you down as a D. There you go. I don't know. Might be the right answer. By the way, I will warn you, sometime before this course is over, there is one where almost always everyone does pick the wrong answer. So if you're that kid who's always trying to just vote opposite of the crowd, that might be your glory moment right there, okay? It did happen last quarter to, who was the one that was always voting that way? Oh yeah, Noah Quinnell, yeah. So he did have his moment in the sun. But he also got rained on like 50 or 60 times before he got that moment in the sun. But yes. Convince me.
Because acceleration is backwards after you release. I got this one.
So you know what? Let's do a process of elimination. How, if this was the correct free body diagram, if D was correct, how would it be moving? No, it's left my hand.
What do you mean?
But just how would it behave?
Oh, keep going.
Can we use words instead of going? Can we use physics words?
Stay in motion.
Sam, what? It would be speeding up. That has to be. Is that what you said? I'm sorry, I couldn't hear you. I apologize. So this has to be wrong because it's not speeding up. I can reject that. What about C? How would that behave if that was correct?
It would stay at the same speed.
In fact, this would be like outer space, or well, since there's an up and down force, this would be like being on ice or on a hovercraft. You're just going to keep going smoothly. So that can't be right. What about B? There's a couple of possibilities. If these two lines are supposed to be the same length, then Marcella, I would argue that it's the same as C. That it's going to keep going at a straight line at steady speed. This line looks a tiny bit longer to me, in which case, if it is, then it has to be speeding up. So I disagree with B, but Matt wants to try and convince me. Go ahead.
See, personally, I believe that all of these diagrams are correct.
Why?
I believe that there should be
I agree.
one
No, I was
where
thinking that.
there's a force going to the right to keep it somewhat in motion.
No, there is not.
No, I know what you're saying.
Push it, right?
After I let it go. Again, after I've released it.
Yeah, so it's moving to the right.
So after I've released it, there is no force to the right.
Are you not pushing it? You're just letting it
After I've released it.
He did a whole like
Okay?
Okay.
So you ready?
It's,
This is important. This is key, Matt. This is good. So we're not talking while I push it. Right now. There's no force pushing it to the right. It has a velocity to the right, but please don't confuse velocity and accelerations. Newton's laws only tells us the direction of the acceleration, and it was definitely slowing down. And it says explain your answer. Matt, what was your response earlier? Okay. I would take that. Yeah.
Is this like?
Well, I would say this. If you wanted kind of like a drop the mic, walk away at full credit, you could tell me which of Newton's laws we just demonstrated, if you know which one it is. But if you can't remember whether it's Newton's first, second, or third, then you could say something like only diagram A will slow down, and I would take that. Anybody know which?
It's the first one.
So if you knew that, you could write Newton's first. But I told you didn't need to memorize which one was which, and I meant that. I will not give you a question where that's the only way you can answer it. So you could also say only A will accelerate left or slow down. All the rest of them will either keep going at a steady speed or speed up. But is that okay, Matt? There is no force to the right. Once you let go of it, its own momentum is going to keep it going. But if it's slowing down, you only need one force to the left, and that's fine. I don't need a force to the right to have it move to the right. Example 5 says, for each of the blocks below, write a vertical force equation, find the force of friction, write a horizontal force equation, find the acceleration. Let's kind of do these simultaneously. So I'm going to just draw a line down the middle of my page. Kind of like that. You know what I should probably do before I even start?
A draw.
I think I'm going to do a free body diagram. Although since they gave me a picture, I'll label the picture. Okay? Harsh, walk through this with me. On the left, what are the forces on this 10 kilogram mass? Harsh, get the obvious one. What else? Bigger, smaller, or the same size as mg? Good. Then I have this 20. Who remembers, what did we call the mystery force coming from off the page? Okay, so I'll say 20 equals F applied. I have a habit, I'll often draw an arrow just to remind myself that I noticed that force so I don't forget about it later. Also because that'll be a different color from the photocopy and it'll stand out a bit more. Is there friction in this question, Harsh? Say yes. How do I know? Because I gave you a coefficient of friction between the object, okay? So which way will friction be? Yep. And I think it's smaller than F applied. I'm not sure yet, but I'll kind of guess, and if I guess wrong, I'll fix it later. Harsh, what about on the right-hand side here? What are the forces acting on it? Get the obvious one. I agree. What else? Bigger, smaller, or the same size as mg?
Bigger.
Okay, first of all, how do I know it can't be the same size? Extra vertical force. Yeah, something else is pushing down, so the ground has to push back up harder. Good. What else? Oh, F applied. What else? Which way? Bigger than the original one, or smaller than the original one, or the same size as the original one? So ready? Friction is what times what? Did the normal force get bigger? So will friction get bigger, smaller, or stay the same? Yeah. I'm a little worried that now it might be so big that we're slowing down. We'll find out though. We'll assume we're still speeding up to the right. Armand, A says write a vertical force equation. So on the left, are we sinking into the ground like quicksand? Are we flying into like Superman? What that really means is everything down equals everything up. Can you turn that into an equation for me? I'll give you a hint. Everything down equals, yes. What about on the right? Still the same idea. Are we sinking into the ground like quicksand? Are we flying into like Superman? That I'm telling you, everything down is going to equal everything up. Can you give me an equation? Note to self, there's an extra down force. Yep. 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 What if instead of that 15 pointing down, what if it was lifting up? You'd have mg equals normal force minus 15, sorry, normal force plus 15, and you'd have to get the normal force by itself if you wanted that. We can handle it. Cool. Nice. Percy B says find the force of friction. Friction is what times what? So mu times the normal force, and part B over here, friction is going to be mu times the normal force. Let's go back to the left-hand one. Duh, I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. In fact, Armand gave me the equation. Apparently the normal force can be replaced with. So you're telling me that I can go mu mg? Keep it down, folks. Thank you. You'd be right. Hey, Percy, what's mu? I don't know. What's mu with you? What's mu? 0.12. M is 10. G is 9.8. I can do that in my head. It's going to be 98 times 0.12. It's going to be 9.8 plus, where was it? 98 times 0.12. It's going to be 9.8 plus 1.96. It's going to be 10.8, 11.76? Yeah? Double check me. Of course, you're all following along on your calculators. Right, Blue Jays?
Yeah.
There you go. What about B on the right-hand side? Well, again, it's going to be mu times the normal force. I don't know the normal force. Or, wait a minute, Percy, do I? What can I replace the normal force with now? In brackets, mg plus 15. So friction is going to be 0.12, 10 times 9.8 plus 15. Do that one in your head, Mr. Duke. Well, maybe. 10 times 9.8 is 98 plus 15 is going to be 113 times 0.12. It's going to be 11.3 plus 2.26, 11.3, 13.3, 13.56. I think I'm right. 13.56? 13.44. No, 13.56. I was right.
Oh, I mean, yeah.
I was right. I subtracted correctly.
You should have said it was called.
I did. Okay. By the way, who was doing the free body diagram with me? Harsh? I noticed that both of these are less than 20, so the 20 is still winning. So good. Our guess was kind of right. C says, write a horizontal force equation. Manchand, what is my horizontal force equation? Who's winning? More specific. Who's losing? Equals? So for the left-hand diagram, it's going to be F applied minus friction equals MA. What about the right-hand diagram? Who's winning? Who's losing? Sorry, who's winning? Friction? How big is friction on the right-hand side? How big is F applied on the right-hand side? Care to rethink your winner? Who's winning? Who's losing? Equals? Same equation as the other one? It's the same tug of war. The values will have changed. But it's a tug of war between friction and the applied force. Cool. Kyle, what's D you want me to find? How would I get the A by itself? How would I get the A by itself over here? In fact, you'll notice I get an identical equation for both. I get A equals F applied minus friction over M. If we plug in numbers, it's going to be 20 minus 11.76, all divided by 10. I can do that in my head. It's going to be 20 take away 11 is 9, take away 0.7 is 8.3, take away 8.24. 0.824? Absolutely. Am I right, first of all? I think I am. And units? What are the units, Kai? Acceleration? And Manchand is right. That wasn't. So here's what I did. I went 20 take. First of all, when you're doing math in your head, you do it in the opposite order than when you're doing it by hand. In other words, I went 20 take away 11, 9. Take away 0.7, 8.3. Take away the 0.6, 8.24. Divide by 10, 0.824. In fact, Manchand, you and I are going to do this one together, okay? So it's going to be A equals F applied minus friction all over M. And if I plug in my numbers, it's going to be 20, take away 13.56 all over 10. Manchand, here's how we'll do it. 20 take away 13.
7.
Take away 0.5. 7 take away 0.5. Now take away the 0.6, 6.44.
Yeah, exactly.
Divide by 10. 6.44 divided by 10. Yep. It's just that easy. Okay. By the way, I mean, obviously, I love to show off and try and do math in my head. I would never do this in my head on a quiz or a test. In fact, on a quiz or a test, I'll type 2 plus 3 into my calculator. Even though I know it's 5, I've made so many dumb mistakes when I'm in a rush. 2 plus 3 is 6. Oh, my brain multiplied instead of adding, and it, stuck the wrong number out, right? So use your calculators. Hopefully you got a good one after your teacher yelled at you last year. Next page. Yeah, you don't have to be moving to have friction. There can be friction on an object when it's at rest because those microscopic hills and valleys lock up when we apply even a tiny force to an object. There's technically 2 types of friction. And when it's moving, when 2 objects are sliding past each other, we call that kinetic friction. When objects are at rest, we call that static friction. So static friction versus kinetic friction. Hey, here's another thought puzzle where we get to vote. Suppose we pull on a desk with a force of 2 newtons and the desk does not move. Which of the following is true? Clearly, static friction is greater than 2 newtons. That's why the desk didn't move. Static friction is exactly 2 newtons. That's why the desk didn't move. Static friction is less than 2 newtons. That's why the desk didn't move. Or static friction, oh, there is no static friction. Once again, we're going to vote. Once again, even if you're not sure, you're going to be required to make an intelligent, educated guess because there's value in guessing wrong. Okay? So again, if I pull on a desk with 2 newtons and it does not move, which of those statements is correct? Who says, Mr. Dewick, this is easy. It's got to be A. Friction is bigger because it's not moving. 1, 2, 3, 4, 5, 6. Anyone else? 6. Jack, were you 7? Who says, no, Mr. Dewick, static friction is 2 newtons? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. By the way, I hear a fairly good explanation, except they keep saying the word move, which drives me crazy. Forces tell us nothing about movement. They tell us about acceleration, but not about movement. Okay? Who says C? Mansions go and talk to the hand now? Yeah, because that one goes over well too. And who says D, no static friction? Convince me. Sam. Why can't it be A? If I pull with 3 newtons on the desk, if I pull with 2 newtons on the desk and friction is 3 newtons, which way must it accelerate? Like, it would be a weird world. Sorry for those of you on YouTube. I'm walking away from the screen. If I pull with 2 newtons and friction is 3 newtons, as soon as I let go, she's getting knocked over. It has to accelerate that way. Okay? Friction is only as big as static friction is only as big as it needs to be to cancel out your motion. So I'm pulling down with 5 newtons. Is the desk accelerating? How big is static friction exactly? Now I'm pulling with 5.2 newtons. How big is static friction exactly? Suppose the biggest this can be is 25 newtons of static friction. If I pull with 24, will it accelerate yet? What if I pull with 25.01? Okay? That's when we'll have an unbalanced force because static friction can no longer cancel me out. But static friction is kind of weird. It'll match you up to a point. It'll be exactly as big as you're tugging until you tug harder than it can match. Question over here.
So how come, so you said you need 25 newtons to move the desk?
Yep.
But if you pull 5 newtons, it doesn't move. So why can static friction be greater than 5?
Because then you'd have an unbalanced force and it would have to be accelerating. It's not accelerating. Newton's first. In fact, if you want my answer here for where it says explain your answer using principles of physics, I would again go to Newton's first. I would say, since it's not accelerating, the forces have to be balanced. The net force has to be 0. You can't have an extra force kicking around. Okay? Now, that doesn't mean that friction can't be bigger. It'll match you. It'll match you. So I'm going to get a little technical now, Matt. You may have noticed, if you're ever sliding something really, really, really heavy, that getting it moving is tough, but once you get it sliding, you can ease up a little bit. And the reason is there's actually 2 types of mu's, 2 types of coefficients of friction. There's a static coefficient of friction when it's at rest, and there's a kinetic coefficient of friction. Usually the static coefficient of friction is a little bigger, but then as soon as it starts to slide, this one takes over. Let me do one with numbers. Example 7. Suppose an object sits on a surface, and we know that static mu is 0.3 and kinetic mu is 0.25. A says determine the force required to move the object in the first place. What might this be a good job for to figure out? I'm going to do a little free body diagram right over here. So here's our little block. What are the forces acting on it? Get the obvious one. Good. What else? Hello. What else?
Sorry,
Normal force, bigger, smaller, or the same size as mg?
same size.
Right now, same size. Okay. By the way, that same size, that's going to start to change a couple lessons from now, and the normal force will almost never be the same size as mg. I'm still doing physics 11, though. It wants the force required to move the object, so I guess it's asking us to figure out this applied force. But what force are we missing from our free body diagram? Friction. I'm just going to label it as friction, and I'm going to just say static if we're not moving, kinetic if we are moving, and I'll flip-flop between the two. What does A want me to say? Can you read it to me again, Mansion?
Determine the force required to move the object.
So if I just want to get this to start to move, I have to overcome which friction?
Static friction.
Okay, so here's my argument. If I want to get this to start to move, the applied force, I'm going to say it has to be equal to friction. Static, really it has to be like 0.0001 newtons larger than that. Has to just outbalance it. Friction is what times what? And this is static friction, so it's going to be mu static times the normal force. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. So the minimum force to get this to move is going to be mu static mg. It's going to be 0.3 times 5 times 9.8. I can do that in my head. It's going to be 49 times 0.3. 49 times 0.3 is going to be 12 plus 2.7. So 14.7, double check. Am I right? I hope. Just hang on. Let me first of all crunch this. Is it 14.7? Now, that 14.7, it won't quite start moving, but you'll be able to feel through your hands, oh, this is ready to slide. If I pull with 14.700000001, now it's going to start to accelerate. Okay? Is that what you're going to ask or point out? I think so. Okay. B. By the way, how hard do I need to pull to get this to accelerate?
0.3.
No, how hard do I have to pull to get this to accelerate?
Larger than static.
More specific, exactly as a number. How hard do I have to pull to get this to accelerate? How hard do I have to pull? 14.7. How hard do I have to pull? Good. B, Owen, the object is pulled with 10 newtons. Find the acceleration and the force of friction. What's the acceleration? Too slow and wrong. How hard do I need to pull to get it to start to move? 14.7. How hard are we pulling in part B? So what's the acceleration? 0. Ain't going anywhere yet. Oh, and how big is friction exactly? Don't say 14.7. How big must friction be exactly, Matt? Yes. Because it's canceling out your pull. That force has to be 0. Oh, what if I said instead of 10 newtons, what if I pulled with 12 newtons? What would the acceleration be? Still 0. We haven't overcome friction yet. How big would friction be? 12, not 14.7, because then we'd have an unbalanced force. How hard are we pulling in part C?
20 newtons.
Now it's going to accelerate. So now we need to do an equation. Who's winning?
The 20 newtons.
More specific, what do we...
Apply is
Who's losing?
friction.
Okay. Problem. Are we sliding now? Say yes.
Yeah.
Then I'm not using static friction anymore. So the first thing it said is find the force of friction. Friction this time is going to be mu kinetic times the normal force, because now we've started to slide. I don't think we need to, because it just wants us to find the force of friction. What's mu kinetic?
0.25.
Times the normal force. I don't know the normal force. Oh, but look. I know the force is the same size as the normal force. So I can go 0.25 times mg. 0.25 times 5 times 9.8. I can do that in my head. It's going to be 49 divided by 4. So 40 divided by 4 is going to be 10. 9 divided by 4 is going to be 2.25. So is it 12.25? You did? I stopped listening to you a while ago. Oh, not meters per second squared, Mr. Dewick. This is a force. Newtons. And now I can plug this in here and get the A by itself. So it wants the acceleration. And that's why, by the way, I gave it in this order. Find the force of friction and then the acceleration, where in part B I said find the acceleration and the force of friction, because in part B we knew the acceleration. 0. So the force of friction was just going to match whatever we were pulling with. Here, no, I have to calculate the force of friction because now we're sliding. Acceleration is going to be F applied minus friction divided by M. F applied 20 minus friction 12.25 divided by 5. 20 take away 12 is 7.75 divided by 5. What's a clever trick to divide by 5? Times by 10 and divide by 2 would work. So 7.75, 77. No, that's way off, Mr. Dewick. Divide by 10 and times by 2. It's going to be 0.775 times 2. 1.4, 1.55? No, I'm off. Is it?
No.
That was more of a fluke. So, I gotta be honest though, Sky, on your test, I'm not gonna give you two different mu's like I did here. We're just gonna treat mu as though it can work for both static and sliding. I don't care. The only reason I'm covering this is because a few years ago I had a student ask, Mr. Dewick, why is it that once I start something sliding, I don't have to push as hard? And the reason is kinetic mu is smaller than static mu. And I'm assuming all of you have tried to slide something really heavy and have noticed that, oh, I got it moving, I can ease up now. Weird. What's the science behind that? I'll give you one possible model. In the same way as if you're on a bumpy gravel road, if you go really slowly, your tires will find every single pothole all the way to the bottom. But if you go at speed, although your tires will hit the potholes, they won't fall all the way to the bottom. They'll coast over the top and just clip the far end, and things kind of smooth out a little bit. We think maybe those microscopic hills and valleys are doing something similar, but that's only if those microscopic hills and valleys are actually what's going on. And there's still some debate as to what's going on with friction. There's several models that explain what's going on. Again, as always, I should point out, friction is not a real force in the same way the normal force is not a real force. There's only 4 forces in the universe. Strong force holds the nucleus together. Weak force explains radiation. Electromagnetism explains everything with electricity, light, and magnetism. And gravity. And even gravity might not be a real force. Einstein argued that it was a curvature of space-time. So it's possible there's only 3 forces. Everything else is a combination of those. So if you're wondering what's friction, it's sort of a combination of gravity pulling down, and then when they collide with those microscopic hills and valleys, that's sort of an electromagnetic repulsion. We don't want to dive down to the quantum level for everything, because it's a rabbit hole you can end up in. Pardon me? But it's true, there's only 4 forces in the universe, maybe 3 forces in the universe, if gravity is not a force, curvature of space-time. What's your homework? Show you what I assigned my other block.
No homework.
Please.
Are we not watching the Big Bang video?
We're going to get there, but first I give the homework. Okay? What are they asking you to find in number one? The friction coefficient. They're asking you to get the mu by itself. And I didn't do one like that with you. I did do them with you last year. To get mu, first get friction by itself if it's not already. And then replace the friction with mu times the normal force and divide by the normal force. Okay? So 1, 2, 3, 4, 5, 6. 7, put a star next to number 7. The star means I'm not going to ask you that on a test. This is the example that has a static coefficient of friction and a kinetic coefficient of friction, like the question we just finished. I'll do one in the homework, but I'm not going to throw it on the test. You can skip 8. 9 is good, or as I like to say, yeah, 9. Okay? That's what I said. 10 is good. You can skip 11. 12, 13, 14, 15, put a star next to it. It's nasty. It's harder than I will ask on your test. It's actually an old scholarship question from Physics 12. But it's kind of a neat one if you think about it the right way. You can skip 16 and 17, but you can add 18.